Okay, great. Welcome, everyone. Good morning. Today we have Guanghao Lo from MIT visiting us. He's a student of Ike Chuang, getting his PhD at MIT. And this morning, well, his interests are in quantum algorithms, also in quantum control theory, quantum machine learning. And this morning, he's going to tell us about how to achieve better quantum algorithms by way of physics.
All right, thank you for the introduction. So if you guys have any questions along the way, feel free to ask. We have quite a bit of time. All right, so we live in pretty exciting times. The first quantum computer, now far from being a theoretical exercise, may soon become a device on which you can actually run meaningful quantum algorithms. And so what this means is that we are now faced with a challenge of how we can compress these quantum algorithms, which previously didn't really pay attention to constant factors, to actually run on very limited hardware. So previously, physics has played a pretty large role in designing quantum algorithms, like Eddie Fahy came up with the adiabatic algorithm. And then we have analogs like the Metropolis-Hastings algorithm, simulated annealing. But it doesn't seem like physics really has had a part to play in the compilation of these quantum algorithms to run on small quantum computers. So today I will focus on how we can actually apply physics to optimizing these algorithms to run on small machines. And in fact, we can get better algorithms by very carefully studying the physics of, well, quantum mechanics, because quantum computers are built on quantum mechanics. So it's natural to expect that intuition in physics would translate into algorithms and compilation. And in fact, I want to make a stronger statement today. I would claim that you can get the best possible physics, the best possible algorithms, at least for Hamiltonian simulation, through a very thorough study of one of the simplest physics, which is rotations on a sphere, or that of a single qubit. And before I continue, I would like to thank my collaborators as Ted Yoder, who I shared an office with for 5 years, and my advisor, Ike Chuang, and without these two, much of this work may never have happened. So let's just briefly motivate quantum computation. There are the exponential speedups that you can get, which are the source of most of the excitement. Feynman originally proposed the quantum computer as a machine for simulating quantum physics. And more after that, Shaw came up with the factoring algorithm that everybody wants to implement on a quantum computer nowadays. And more recently, we seem to have interesting developments in quantum machine learning, which in some instances seem to have an exponential speedup, although that is still a subject of much research. And there are also other interesting results like quantum approximate optimization and sampling. So aside from exponential speedups, it's also quite easy in a sense to get less exciting polynomial speedups, but also quite relevant. Like Grover came up with the Grover search. Then there's also, in some cases, a quantum Metropolis-Hastings algorithm. And once again, we have machine learning. And there are many more applications of where quantum computers can provide very interesting applications. So now the main problem we face today is that the first scalable universal quantum computers are within sight. We have architectures of trapped ion superconducting qubits, but their projected capabilities will be somewhat limited. For example, we have 50 to 100 physical qubits and some thousands of single and two qubit gates. But this doesn't include aspects like the logical layer for fault-tolerant error correction. So if we want to run any of these algorithms on the small quantum computer, there's a lot of work we need to do to actually make meaningful instances possible. So this problem of compiling algorithms to run on quantum computers is that of quantum compilation. There you are faced with certain constraints, like your algorithm is a unitary that you need to compile into a universal gate set. Maybe your architecture could impose constraints like maybe nearest neighbor interactions and all that. And so this is a pretty big problem. And one large aspect of quantum compilation is the computation of classical functions. So let's say on a classical computer, you might have a number in your n-bit register, and you might want to, say, compute its exponential, or maybe compute its square. And a straightforward way to do this is using phase estimation, where your phase is the input variable, and you want to compute f of this phase. So phase estimation then encodes x in binary here, and you could perform f of x in binary here by translating well-known classical circuits in regular computers and making them reversible, then applying them on a quantum computer. So this approach is pretty intuitive, and it makes a lot of use of the bulk of knowledge that we have already learned about through developing digital classical computers. But the problem with this approach is that there's no a priori reason why simply translating a classical circuit to the quantum case would actually create the optimal way to compute functions. It's like, is binary really the best encoding for storing all of this information? And also, when we have gadgets like phase estimation and making classical circuits reversible, there's a lot of overhead in the ancilla. And you could easily exceed the very limited qubit budget you have on early quantum computers. So we would like to find a way, a different way to look at this problem of computing functions and compilation. And I claim that physics provides one possible way forward in a very different direction. So just as how physics was invaluable in designing quantum algorithms, I would like to claim that physics is relevant to compilation, but it's a bit hard to see the connection here, because when you compile your algorithms, you're kind of performing a discrete optimization problem. How does this really relate to physics, which is continuous and deals with an entirely different set of controls and constraints? So I would like to motivate the idea that we can look at physics to motivate a different kind of encoding, a different way to compute these functions. And the end result is that for certain functions, we can actually compress many ancillar qubits into just one ancillar qubit. So this would be pretty useful. This would be pretty useful. And it seems like, a bit far-fetched. I mean, if you have an n-bit register here, how could you possibly encode those n bits into a single qubit? But it turns out that you can restructure some algorithms to actually make this idea possible. In the following, I will motivate and justify this approach with a series of 5 problems. In the first 2, I will talk about the physics of one-qubit rotations to show how they can motivate a different approach of how you can compute functions on a quantum computer. So these 2 examples, they solve 2 very physical problems. One of them is compensating for systematic control errors in quantum gates at the physical level. And the other one is how we can think of these single qubit rotations as computing functions that allow us to perform microscopy that is much better than classical limits. Now, these are examples of physics and control theory. If we want to apply them to quantum algorithms, then it seems natural to look at algorithms that naturally have an algebra that is isomorphic to single qubit rotations. A very natural choice would be quantum search, which we know are a product of reflections, and a product of reflections becomes rotations in SU2. We can apply the ideas in control theory to then devise a different kind of quantum search, which is one with a fixed point, in which if you apply this search for longer periods of time, it converges to the answer rather than rotating to the right answer, then rotating away as you apply it longer and longer. Now, before we can generalize these ideas to apply to more quantum algorithms, we need a way to actually understand what is going on in these single qubit rotations. We need a systematic way to devise optimal control policies and to characterize the functions that we can compute in this manner. So this is a 4th problem where I talk about how we can efficiently synthesize optimal control policies on a single qubit. And at this point, this seems to be of pretty limited scope. It requires algorithms that have this natural SU2 algebra. But many quantum algorithms do not naturally have this structure. And so we then ask not what single qubit rotations can do for us, but what we can do for them. In this case, we can build single qubit rotations, or at least an algebra that is isomorphic to them, into quantum algorithms. And the most prominent example here is one of Hamiltonian simulation. So since Hamiltonian simulation is promised to be QP complete, which means that all of the exponential speedups you can realize, like Shor's algorithm, can in principle be realized as instances of Hamiltonian simulation. This kind of indirectly says that these ideas can be translated to all quantum algorithms through the vehicle of Hamiltonian simulation. So the first example is that of quantum gates where we experience systematic faults. So at the physical level, a single qubit quantum gate could be implemented by, say, shining coherent light on your ion. This drives oscillations between the ground state and the excited state. And if you apply this laser light for some time, it generates a rotation. So here's a nice animation. If we start in the ground state, as we apply the light for more time, it rotates to the one state. And if we choose a rotation angle in the applied unitary to be pi, we get a NOT gate. But at the physical level, you encounter all kinds of errors. For example, perhaps your laser intensity was a bit too high. Maybe you applied your laser for too much time. And so a common error that might arise is that of systematic over or under rotations. So here you have a faulty NOT gate. It doesn't quite rotate by pi. It goes from the zero state and it doesn't reach the blue dot over here. So one common way to characterize the performance of these gates is to look at its fidelity. In this case, we are looking essentially at the distance between the applied unitary, the faulty NOT gate, and the ideal NOT gates. And for the NOT gate, this turns out to be the x components of the applied unitary. And if you look at the fidelity as we apply our rotation longer and longer, it gets closer and closer to the perfect rotation. Then if it's a bit below or a bit over, you get an imperfect gate. And one way to characterize the robustness of these gates to systematic errors like this is to look at the correction order, which is how does the infidelity scale as you deviate away from an ideal rotation. So the obvious way to fix this error would be to measure this over-under rotation. And then in your experiment, you might turn a knob to perhaps boost the time or boost the intensity to bring this closer to the blue dot. But this is not always possible. It's also not always practical. In one simple example where it's impossible, you could imagine that you could have an architecture where you have an array of ions and they're all illuminated by a beam of light. But this beam of light is non-uniform. So if you wanted to apply a NOT gate to all of these ions, it would be unavoidable that some would rotate more than the others. But that turns out to be a very nice solution. So here we have rotations around the x-axis on the sphere. You can convince yourself that without knowing in advance what the ion rotation is, no amount of rotations will ever bring you close to the blue dot. Maybe you might get there if you apply n rotations and then happen to be just the right amount to bring you there, but that would not happen. However, if we allow ourselves more control over our system, instead of rotations about just the x-axis, if you allowed ourselves rotation about, say, the xy axis, in this case, we have these rotations, they all rotate by the same amount, but the axis is different. We can bring the red dot closer to the blue dot. So this is called a pulse sequence because we have a sequence of gates. And in order to apply these rotations about different axes, we need to assume certain resources available to us. In experiments, it's quite common to assume that you have perfect phase rotations. And since you can conjugate your faulty rotation about the x-axis by two phase rotations, you can rotate the axis of R through a sequence of phases interspersed by our faulty NOT gates. And this is pretty amazing. It's like without knowing what the error is, you are using the non-commutative geometry of the sphere to cancel error terms and bring the red dot closer to the blue dot. Like previously, the fidelity here was quadratic, and now it is quartic. So, we went from one sequence to one gate to 5 gates, and perhaps if we had longer sequences, we could have higher orders of correction. it turns out that this is actually a pretty bad sequence. Using the same length, we can get like order 6 correction. And since gates on a quantum computer are very expensive, we want to use as few gates as possible. And previous work, they studied how efficiently you can get high order correction with sequences of different lengths. And so it turns out that you can get exponentially good gates with polynomially many gates. Here it's n cubed using a method that's analogous to the compilation of single qubit unitaries into H and T gates using the Solovay-Kitaev theorem. And more recently, you have methods to bring this down to almost linear. So,
how does it compare to the sequences known in like NMR, for instance?
So
how does it fit into that table?
it turns out that all of these sequences were initially considered in NMR applications. So, like in this work by Wim Paris, he considered the problem of you have inhomogeneous spins in your magnetic fields, and you want to apply like a uniform population inversion to all of them. So using this method, you can kind of apply a sequence of gates to bring the error down and suppress it to higher orders. It was only more recently that people realized that these NMR sequences are actually very relevant to applying these gates at the physical level.
Refocusing sequences? Okay.
So different physical systems have different errors, and here I'm focusing on this particular error where it manifests as a rotation that is too big or too small.
Is it specific to Z rotations though, or will this work for any kind of...
So I'm considering a very specific set of errors and a very specific set of resources. So yes, this does apply only to perfect Z rotations.
So I'm just kind of curious, why would you choose to use one of these high-order pulse sequences instead of OCT for single qubit rotations?
Sorry,
Why would you choose to use a high-order sequence as opposed to OCT?
Well, so one nice feature about this sequence is that they are formed of discrete gates. In OCT, usually one is concerned with the continuous, like Hamiltonian that's continuous. So on one hand, implementing a continuous Hamiltonian and characterizing it at every step could be a bit more difficult. So by breaking up into these discrete steps, each step can be characterized separately, and so you can kind of get a better assurance that if the parts individually work well, then the end result will work well. But this is actually just another form of OCT. In OCT, you usually discretize or control into steps. And what is this but large discrete steps? So here we have basically OCT under the assumption of discretization that, so like not continuous. Basically the same thing with different assumptions.
Are all the three methods ancilla-free?
Oh, these are all ancilla-free. So they are all physical rotations on a single qubits.
Right. I'm wondering about the Jones's model.
Those. So we have a similar sequence here. It's just longer. Instead of maybe 5 R rotations here, we have L rotations, all on the same qubit. All on the same qubits. Yeah. So 2 years ago, we came up with sequences of optimal length. And like how the optimal compilation of single qubit unitaries into H and T gate scales linearly in the correction order, we find that you have a similar analog here where the correction order scales linearly with the length of your sequence. And so if you were to look at how the fidelity varies with these very high order error suppressing sequences, the purple line here is that of a single pulse. It's the sine curve. But as we use longer and longer sequences, it gets flatter with respect to errors about pi. So this is getting more robust to errors. And just for to give you an idea of what it could look like, here's a sequence of 17 rotations. And the blue dot, which was initially here, is now basically exactly on the red dot. So that's pretty nice. So previously, we did this by reducing the design of this optimal control sequences into a set of polynomial equations. And then solving a general set of polynomial equations actually turns out to be extremely difficult. But later on, I will show you how this can be done efficiently. Now, we have had a sequence of gates and they produced a fidelity that was pretty flat, about theta is pi. But there's another way to interpret such sequences. You can think of them as computing a function. So the phases here, they specify a program that computes this quantum response, which is the target unitary, as a function of theta. So this can be analogous to how on a classical computer, if you wanted to specify a function, you might say, well, here's a polynomial and here's a set of coefficients and here's the output. So you can think of the phases as being analogous to these coefficients. They specify a program. And we want to take the interpretation that these are not like Pao sequences, they are composite gates that compute functions. So before we can actually use this, we need to understand what possible response functions we can actually implement with such a sequence of phases. So since these are single qubit rotations, we can always decompose them into some universal basis. In this case, we have the Pauli basis. And the coefficients of these Pauli bases would be some functions of the rotation angle. And so by choosing these functions, we could perhaps compute something that's more exciting than just something that's flat here. Perhaps by an optimal choice of these functions, maybe we could do some really interesting things. And just for an example, in the NOT gates, the fidelity is actually this coefficient here squared, and this is the optimal function that is implemented. It looks like this, it's very flat here, and let's see what more you can do with it. So now I'll talk about how we can think about different functions we can apply and their different applications. So one very neat application is in microscopy. Sorry?
What at the bottom? Was it in n goes to infinity limit?
This is
in terms of length of the sequence you want.
So this is for any finite L. Like let's say if you had a length 5 sequence, you would choose this to be 5, and then it would be a sum over 2 terms. And similarly for longer sequences, you'd have more terms here, and as you include more terms, it gets flatter and flatter.
And so the specific curve is for which value? Well, I would imagine.
Oh, this is 25.
25.
If it was, say, 1, you get your nice sine curve over there. All right, so the next important application is how we can image point objects with the fewest resources, in this case, time and energy. So for those who took Physics 101, you might recall that if you have a point object that scatters light and you irradiate it with coherent light, these point objects, they will re-radiate, and because of the diffraction limits, which is how light interferes with each other, you can't refocus it precisely onto a point in your camera. Rather, what you get is that from each point source, you get a pretty vague blob here. So this scatterer here has an intensity distribution that varies like this here. And then the other blob has another distribution here. And when you add the two together, you get the image on the camera. And Lord Rayleigh studied this problem of when we can resolve these two objects. Like when can we say that they are separated and distinguish them? Because if they were very close together, you just get a very big uniform blob and you couldn't really tell which is which. So Rayleigh says that these two are resolvable if they are separated by more than the wavelength of the illuminating light. But if we focus on a different question, which is how can we estimate the positions of these point objects, we can accumulate statistics from these scatterers, and then we could try to fit functions here to estimate the mean of their positions. And then we can ask the question of how much time and energy does it take to estimate the positions of these point objects with a precision that is much less than the wavelength of light. So this is a question that has, I guess, applies to many areas of physics, biology and chemistry and all that. And so maybe it's not surprising that the solution called super resolution imaging won the Nobel Prize in chemistry. So the idea there is that in the previous case where we just have these 2 point objects, it's a very classical problem. Light falls on the object and it scatters. But if we were to use some quantum properties like coherence, we could do something more creative. We could say switch these scatterers on and off. For example, perhaps you could use quantum control to sometimes switch this off and switch this on so that when it's irradiated, only this one will scatter light. And if you do this, you can get a noise-free distribution of the light that comes from one of these without any noise from the other. And if you were to repeat this procedure, sometimes you could switch this one off and switch this one off, and you could repeat the same over here. And so by just gathering statistics over counts, you can see that the average number of counts slowly converges to something that resembles the ideal intensity profile. And by taking the mean of the positions of these, you can find the average position. And we might have learned from statistics that the standard error in the mean by averaging scales with the square root of the number of counts. So here, the wavelength of light sets the length scale of how well you can estimate positions. And this estimate has a precision that goes down as you take more and more time in your estimate. And so if enough time, you can get very precise measurements using light that otherwise would just give you two very vague blobs. So if we were to consider how much time and energy we need to accumulate to get an estimate at some precision, since the number of counts, since each photon requires some time and also requires some energy, we can solve for counts, and we find out that the amount of time we need scales quadratically with the inverse of the precision. But this only achieves something known as a standard quantum limit because it is inherently a result that you get from accumulating statistics. It only partially exploits quantum coherence. It doesn't fully exploit, like, in a sense, the full power of quantum mechanics to this problem.
To that extent, I mean, I'm kind of curious if this is even asymptotically needed in the first place, because you still have some overlap between the two peaks, as you can see in the previous picture. So could you just use standard hypothesis testing to end up getting the same scaling?
So that's an excellent question. The main issue here is that with noise. So in an ideal world, you could just fit all of these to, n Gaussian blobs, and then you're guaranteed that if you apply statistics, you accumulate enough counts, then the standard error of the estimates of all the positions of these blobs will still go as 1 over the square root of n. But in practice, there are a lot of other systematic errors that could arise. For example, your camera could be very discretized, so you could try to fit to the Gaussian blobs, but then there are various practical problems, like maybe your camera could be misaligned, maybe you could have noise from other sources. So this will introduce a bias in your estimates. But this here, it kind of reduces the impact of these noises. You could think about it as maybe it's a very big reduction in the constant factor, but it is big enough that it is actually very important. So anyway, previously we found a way to fully utilize quantum coherence to improve this by a square root of factor. So this achieves something called the Heisenberg-Limit, where the time taken to achieve a precision estimate scales linearly in the desired accuracy. And this, as with the case of composite quantum gates, uses a sequence of single qubit gates. So the idea is that instead of computing a function that is really flat about some target rotation angle, we could instead compute a function that is very sharply peaked. So here, if we had a single pulse, we could compute a function that's just sine, it's pretty broad. But using longer sequences, we can implement functions that have very narrow peaks. And it turns out that the width of these peaks scale as 1 over the length. And so using these sequences, we can very selectively excite or switch on and off these scatterers. And in this case, once you can do so with this kind of linear scaling, you can actually just directly do a binary search for their positions. So this is like, let's forget about statistics. Let's just use the full quantumness that is available to us to make very narrow excitation profiles and, just do a search. And this has also been implemented by some of my collaborators at Lincoln Labs.
You mentioned you use it for imaging, determining the distance between two locations.
Yep.
Could you use it for beam shaping also?
So that's a good question. Here, this is kind of like you have maybe a Gaussian beam, and then it produces some excitation profile. Now, if you choose the right excitation sequence, you can reshape it to produce some other desired excitation. So it's a kind of beam shaping, but it's operating at a different kind of physical level. Instead of the hardware level, it's like you could think of it as a logical level, but it's still very much physics.
But it's not impossible because I could make structures that are smaller than the wavelength of the light.
Yep.
Is it possible?
It is possible. So I guess that's maybe the most exciting part of thinking of sequences as functions. So we are no longer limited by our intuition of classical physics because it is now all quantum. We no longer need to say that, oh, these peaks, they must be the wavelength of light. We can just implement a function that computes something that's very narrow. And if you put in more time into these sequences, you can compute more and more sophisticated excitation profiles. And a good question is, if I wanted to have some arbitrary excitation profile, how many sequences do I need? It's like saying, what is the cost of computing this function? So that's a question I'll address later. So just to show how this is another example of computing functions. Sorry
to pull you up in this one slide, but can you go back a second? So I read a little bit about the case of Heisenberg-Limited metrology, when you have like a bunch of particles, you put them in an entangled state, and that allows you to, for example, pick up the background field in the Heisenberg-Limited case. And I also know that the Heisenberg-Limited scaling dies with noise. In this case, you have, it seems like quite a different setting because you don't have, you're doing these, you're applying things over time rather than having like an entangled state in space. So what's the analog? Do you use entanglement in some way here? Or?
Right, so this is entanglement free. We can think about it as a form of phase estimation. Like in some implementations of Shor's algorithm, they use scatter phase estimation where you only have a single ancilla. So the idea here is similar, except that we want to do something that instead of generating many sine waves, just generates a very sharp excitation profile. So in principle, you could not use all of this funny control. You could just implement lots of sine waves, and you could activate some of these on and off. And then you could, in principle, say use techniques such as compressed sensing to extract the positions of all of these ions. But the problem there is that it's similar to what we saw for the classical case where you might have systematic biases, and this could make it difficult to identify these positions using like compressed sensing and collective measurements of all of them at the same time. If you were to also study the compressed sensing algorithm more closely and look at the scaling, it doesn't achieve Heisenberg scaling. It's like Heisenberg times log factors. Maybe log factors aren't very exciting, but it's not exactly optimal. So anyway, to show that this is just another example of how a sequence of single qubit rotations can compute a function where the function is defined in these coefficients. The case of imaging is solved by choosing the functions C and D here. The transition probability is the probability of going from the 0 state to the 1 state, and so that would be C squared plus D squared. And the optimal choice for this problem turns out to be the Chebyshev polynomials. So one example here is plotted. You can see that they all have these very small ripples that are bounded by the desired probability of errors, which is error of illuminating other neighboring scatterers. But they have this very small narrow peak over here, and the width of this peak, as described earlier, scales inversely with the length of the sequence. And this probability of exciting other neighboring scatterers is logarithmic, so you can make this very, very small very efficiently. So it's like one way of suppressing noise. All right, so I've described two examples of physics where by thinking of them as computing functions, we can get optimal behavior for solving physical problems. We now want to show that we can actually apply this physics and translate it to quantum algorithms. So the natural way to do this is to look for quantum algorithms that are already isomorphic to single qubit rotations. And the standard example of this would be quantum search. By choosing the right functions, we can modify quantum search to exhibit more desirable properties, such as a fixed point. So this problem of why a fixed point quantum search is useful was described in, I believe, a paper by Views as Overbaking the Quantum Soufflé. I'll briefly go over what the quantum search is. You have an unsorted database of n items, and you have an oracle that marks some of these items with a phase. So in order to perform the search for these marked items, you would prepare the uniform superposition, and then you would aim to prepare the target state, which is a uniform superposition over just the marked items. And we do this by doing a sequence of reflections about these start states and target states. So this can be visualized on a block sphere. Here it's projected onto 2 dimensions. We have the target state here, which is what we want. And our start state has some finite overlap with the target state here. And so if you were to represent it as an arrow here, it would have an angle theta with respect to everything that's not the target state. So the Grover search works by reflecting about the target state, and we get this here. Then by reflecting about the start state. So this goes here, and this goes here. And the product of these 2 reflections turns out to be just a rotation by angle 2 theta here. And our start state, which had small overlap with the target, now has a larger overlap with the target. So by applying this a few times, we get closer. But if we do not know how many times to apply this rotation, we might overshoot. So here you can see the success probability. It goes up and it goes down. So like the classical souffle, if you take it off your oven too soon, it hasn't risen up quite high enough, and maybe it may turn out to be a failure. If you take it out a bit too late, it may end up being burned, and that's also a failure. You need to take it out at just the right time so that when you measure it, you get what you want. So the problem here is, how do we get the perfect souffle all the time using the fewest resources available? Now, there are many ways to solve this problem. Like one could simply estimate what the overlap here is. But the problem with this is that it requires you to, prepare many soufflés. You might undercook many of them and burn many of them. And if you were to just throw away all these soufflés, you'd probably lose your job as a chef. So we can, take a similar picture in quantum algorithms. It is wasteful to discard states when we don't have to. We shouldn't have to re-prepare them all the time. Ultimately, the asymptotic scaling will turn out to be no different from just directly estimating the phase, but perhaps a less wasteful approach could lead to a simpler algorithm that has smaller constant factors. So to formalize this idea of what we mean of getting the perfect souffle all the time with with the fewest resources, the fixed point quantum search considers a problem where you want to prepare the target state without prior knowledge of the number of marked items. So in this case, this means that the overlap is unknown. We only have a lower bound for the overlap. We want to create our souffle with very high success probability, and we want to do so without any classical repetition. So no measurements in between and no additional state preparations. So here we just have a list of what has been done to achieve this. We had the original Grover search where we had to know the number of marked items in advance. Then by doing quantum counting and repetition, you can estimate n and obtain the quadratic scaling of Grover search. Then in 2005, Grover came up with an algorithm that meets all of these criterions. So without knowing what the exact number of marked states was, he had an algorithm that was fully coherent, no intermediate measurements, that if you applied it many times or for longer and longer times, the souffle would slowly converge to perfection. So in this case, the error of obtaining the perfect souffle is logarithmic. But the key problem here was that in going from the fixed points, in implementing this fixed point search, the quantum scaling, which is most desirable, was lost. And in fact, he came up with a no-go theorem saying that this was optimal. So this seems to suggest that maybe it is impossible to get fixed point quantum algorithms. And intuitively, that kind of makes sense because quantum algorithms are unitaries. So if you apply the same unitary over and over again, you just get rotations that go on and on. Like, why should they converge to a fixed point? So anyway, this no-go theorem turned out to only be for the scaling and error. And so more recently, Aronson came up with a fixed point algorithm that satisfied all of these criterion. It retained the quadratic scaling, but then it lost this exponential scaling in the error. So like while you could get your perfect souffle, you had to put in a bit more effort than what was ideal. And recent...
How does that coexist with the no-go theorem?
The no-go theorem only applies to the error scaling. It also only applies to a certain kind of like optimality criterion. And we can violate this no-go theorem by choosing a different optimality criterion that still satisfies these conditions. So here we have one of our recent results for this. We achieved the same quadratic scaling, and we also achieved the optimal scaling and error. So this is fully coherent. It doesn't use intermediate measurements. It doesn't require you to re-prepare states. So if you were to look at the constant factors of doing this fixed point search, it also turns out to be pretty small. So to compare a non-fixed point algorithm with the fixed point algorithm, in the non-fixed point case, you could apply some number of those Grover iterates, those reflections, and the success probability would oscillate up and down. And as you apply more and more Grover iterates, it would oscillate more and more severely. And so if your initial overlap was this black line here, it would be kind of up to chance as to whether you got high success or low success. But by engineering the right sequences in SU2, instead of rotations about just a single axis, we can use the same analog for Pau sequences where we exploit rotations about different axes to build more interesting behavior. So here in the optimal fixed point search, we construct a sequence of unitary rotations where if you apply the sequence for additional times, the success probability goes up and then it stays up. So as you increase the number of iterates, it doesn't get worse.
How does this coexist with the no-go theorem? Which assumptions do you set that?
So in the very first example, for Pau sequences, we had this very flat kind of excitation profile. That is the optimality criterion of maximal flatness. Here we use the optimality criterion of bounded error. So it's like the Grover's fixed point search used the maximally flat criterion, and if we introduce these ripples here, we can actually do much better. So this algorithm was optimal for flatness, but here we have a different criterion with different properties.
So I got a question. So if, say we were to follow the standard prescription and amplitude amplification for this type of thing, where you do an exponential search on larger and larger rotations and then use a Chernoff bound, don't you end up getting exactly the same asymptotic scaling out of this? I know it's not fixed point, but...
Yes, you do. So this is, I guess one example of that would be maybe quantum counting. So yes, you can get the exact same scaling, but here we are concerned with like making algorithms as small and as efficient as possible to like compact them. So we want to minimize all of the additional overhead. And here we want to avoid all of that. And with an algorithm that is fully coherent, that doesn't need you to discard and prepare states, perhaps we can get something that has less overhead. Like in terms of the scaling, it isn't better, but we are interested more in how we can like make them as efficient as possible in terms of constant factors.
Sorry, can I clarify? So are you trying to say that you're saying that you use like much less qubits for your approach than like by using like if you use phase estimation?
Yes. Okay, so this depends. There are many ways to perform phase estimation. One way is to use a cutoff approach where you just measure and like project onto the target state, and then you perform this many times for a different number of rotations. The other way, which is fully coherent, is to embed Grover search into a phase estimation algorithm where you do phase estimation on the angle of rotation. So in that case, that would need more qubits.
You mentioned, back to the constant factors, you were mentioning that there's constant factor differences. Are you going to discuss what those differences are?
I will discuss them not for the case of Grover search, but for Hamiltonian simulation.
Question, in this Grover paper, right, the sequences you get, they are very irregular. They all look like a fractal, basically, right? When you want to
So
100%. To me, they look very irregular because they get longer and longer. And if at a given time I want to know what pulse to apply next, it's kind of hard to figure out just from the location. At least it's my understanding. I wonder in your sequences where you get the square root of n speed up, what is that a nice structure to this?
yes, that's actually a very nice structure. So the Chebyshev polynomials, which I haven't gotten to, but these are actually just Chebyshev polynomials, they form a semi-group. So if you were to nest Chebyshev polynomials recursively, you get more Chebyshev polynomials. So it turns out that you can embed a short sequence for Grover search into a longer sequence for Grover search, and the phases can all be obtained in closed form.
You have to compute them on the fly, or
So this can be done classically. The phases are a list of numbers that would determine the sequence of rotations you implement. All right. So anyway, we can apply the same physical intuition that we had for pulse sequences to this Grover search by mapping the parameters of the search to these phase rotations and these R rotations. So the phase rotations are partial reflections, and the R rotations here, they are just a state creation operator. And different choices of functions here, they solve different problems, they lead to different algorithms. The success probability is just going to be 1 minus this squared and this squared. So Grover search is obtained if you choose this function to be a sinusoid, so you have the dotted line oscillating. And the fixed point search if you choose the maximally flat criterion, where you have cosine raised to a high power, and so you get this flat transition profile here. And optimal fixed point search is obtained by choosing the Chebyshev polynomials, where you have oscillations. So, Grover, these partial reflections, they can be applied to more than Grover search. We could compute different functions here, and it turns out that OR, which is Grover search, is just one of them. You could say compute majority, which is a fraction of Mark states greater than half or less than half. And it turns out that you can basically achieve constructively polynomial lower bounds for symmetric Boolean problems. So in all of this, I have kind of sidestepped one very important point. I've only said that you can choose these functions to solve problems, but I actually told you how to compute their implementation. Like the choice of functions is a program, and the compilation of these functions is a phasors. So how do we compute those? And furthermore, what functions can we choose? There I just put a few functions out of the hat. I said, oh, this is flat, that has ripples, but is there a systematic way to characterize all these possible functions? So previously, this problem of designing quantum response functions was done on a pretty ad hoc basis, meaning that there wasn't really a unified, systematic, efficient way to compute them. So let's formalize this problem of computing functions as saying that we have an objective for the target response function, and we want to approximate this objective function with a small error using the shortest sequence of phasors. So we need to address a few questions before we can actually use this as a useful procedure for designing algorithms. So first, we need to characterize what are valid choices of these functions. We need to ask how to choose these functions. And once given these functions, we need to show how we can compile them efficiently from any choice. And then to actually use them in algorithms as well, we need to figure the complexity of how many phases we need to compute. We need to compute some desired function. So from those previous three examples, this picture of viewing sequences as functions is applicable to quite a few problems. And the sequences are transferable between applications. Like the application of imaging was transferable to the application of fixed point search. However, these optimal sequences, except in very rare situations, can only be found by brute force. So while some optimal sequences, like we had for imaging and for fixed point search, could be found in closed form, and they were optimal since they achieved the optimal scalings, they are special cases. For general choices of these functions, usually you can only do things like gradient descent. So like a numerical search over all the spaces to minimize the output to your objective. And this brute force search has an exponential runtime. If you are willing to accept suboptimal scaling, you can sometimes use heuristics for certain applications that can give you sequences that can be computed in polynomial time, but they are not optimal. So here we are concerned with the problem of optimal sequence design, and we want to do so in polynomial time. So recently we came up with a systematic methodology that solves this problem. To understand how this works, we first introduce some definitions. A choice of these response functions is achievable if the ABCDs can be implemented by some set of phasors, because not all choices are valid. For example, if I chose C to be greater than 1 at some point, that would correspond to having a transition probability that's greater than 1, and we know that's not possible. So clearly there are some restrictions on what ABCD can be. And choosing all of these functions ABCD simultaneously can also be quite challenging due to other auxiliary constraints that apply to all of them simultaneously. Like, since U is unitary, A squared plus B squared plus C squared plus D squared is equal to 1. And so if I were to just choose A and C, it seems kind of hard to also know how to choose B and D efficiently. So another definition is that a partial choice of some of these functions is achievable if we can find some set of phasors that implement them in a manner that's consistent here. So in order to solve this problem, we have 3 results. So first, given an objective function for 2 of these functions here, the best epsilon approximation can be computed in polynomial time efficiently on a classical computer. And once you have this partial choice here, you can then compute the remaining unspecified choices in polynomial time, and these 4 functions now will be achievable. So they are not like random functions, they are something that you can actually implement. And once you have this fully achievable set of ABCDs, you can then compile them into their implementing set of phasors also in polynomial time. So by following these 3 steps, we have a systematic methodology that's efficient for designing these functions over here. So now, previously I pulled out the maximally flat sequences for NOT gates out of a hat, and I also put the Chebyshev polynomials out of hat. But now you can actually derive them constructively as the solution to an optimization problem, and you can find these solutions efficiently.
Is there any restrictions on the range of thetas?
So theta, since all these rotations are identical here, all these thetas, they are periodic. They go from 0 to 2 pi. All right. So this bit here is a little dense, but I'll just go over it briefly to characterize exactly what kind of functions we can implement using a sequence of single qubit rotations. So since these rotations here, they are sines and cosines, if you were to look at a sequence of sines and cosines multiplied together, then the coefficients here, they turn out to also be polynomials in sines and cosines. Like this A of theta here is a trigonometric polynomial in cosine theta, and then say C and D are trigonometric polynomials in sine of theta. And
Can you remind what Z boxes are?
So the Z boxes, they are phase rotations. So you can think of them as constants. So if you intersperse constant matrices multiplied by sines and cosines, and you expand it, you get like a product of sines and cosines. So more rigorously, these ABCDs, they can be implemented by some choice of phasors if they are all real, they are polynomials, and they are of degree at most L. Now, when these rotations are 0, so like theta is 0, you would expect this gate to implement identity, because, or at least, and so when when theta is 0, we want to get an identity gate. So like A at theta is 1, A at theta is 0 is equal to 1. Then some other constraints are on the parity of these polynomials, whether they're even and odd. This here deals with unitarity, they square to 1. And because it is hard to choose all of these 4 polynomials simultaneously, here we also have a theorem that fully characterizes any partial choice of these polynomials which turns out to be pretty intuitive. So like if I wanted to just choose B and C, which is a case relevant to NOT gates, it turns out that any choice is valid so long as B squared plus C squared is less than or equal to 1. So basically any bounded function that where B and C have like opposite parity. So that's pretty general. And the query complexity of implementing any target function here then can be viewed from the perspective of approximation theory. So since polynomials are dense in the space of real functions, we can then say that if you want to implement some target function, you simply find the best polynomial approximation to that function. So this can be done efficiently using algorithms like the Ramez algorithm. And the scaling of how many of the degree of these polynomials is also very well understood. Like say if f was smooth in the first k derivatives, then the length of the sequences you need to use would have an error that would have a length that scales as 1 over the error in this form. And if the target function were to be analytic, you could even get exponential scaling in the error. So this provides a very elegant way to view how you can best implement different functions on a quantum computer. It's like we can draw from these theorems, and instead of looking at phase estimation and looking at classical circuits like compute functions, we can just say that, well, here's a function, it has some profile, and this is exactly the complexity.
All right. If you do Ramez, then the interpolation points are not predetermined, right?
Mm-hmm.
They will basically pop out of the optimization.
Yes.
Correct?
Correct.
So how does that fact get reflected in the sequence?
All right. So this actually gets a bit more complicated if you actually consider the algorithms for finding these optimal approximations. So the simplest approach, where f is fully defined over the interval from like -1 to +1, can be obtained by Chebyshev interpolation. And what this means is that you actually define your interpolation grid, you find the overlap of the Chebyshev polynomials, and then this gives you a Chebyshev polynomials where the coefficients are this overlap. And the error of this procedure actually turns out to be exactly this, up to pretty small factors like logarithmic and L. In terms of the Ramez algorithm and other algorithms, there it's slightly different. You do not define the function over the whole interval, but you only define it over sub-intervals. Like maybe you might only be interested in the behavior in some small range. So those algorithms automatically find the interpolation points that best minimize the error in these sub-intervals. There are some subtleties implying these, but they have been very, very extensively studied because polynomial interpolation and finding best approximations is used extensively in, say, classical finite impulse response filters, and we can transfer all of those methodologies to this case. So it's like borrowing from a large field that already exists to the quantum realm. All right, so now we have, I hope I've convinced you that treating single qubit rotations as a form of computing functions is good for something. We can solve some interesting physics problems, and we can solve some, improve a little on some algorithms that already naturally have this kind of single qubit structure. But not all algorithms have this kind of SU2 structure. It's like there's really no reason why you might expect these methodologies to apply to other quantum algorithms. So if we cannot find quantum algorithms that naturally have this structure, then perhaps the natural solution is to build this structure into quantum algorithms. And if you can build this structure into quantum algorithms, then you could use these methodologies to then efficiently compute functions and get like interesting behavior. I give you a good example here through Hamiltonian simulation, where by computing the right function and by casting Hamiltonian simulation into a problem that has this algebra, we can get the best possible Hamiltonian simulation algorithms. So when I say best possible and optimal, I don't just mean like in asymptotic scaling, like for large parameter values, but it is optimal up to a constant factor of just about 2 over the lower bounds for an inquiry model. So Feynman proposed that since nature is based on quantum mechanics, it is quite natural to think about simulating nature with a quantum system. So the reason why this is natural is because if you have n qubits, then there would be an exponential number of states. Simply writing down these states on a classical computer would take exponential time. And since this problem is BQP complete, it is very unlikely that you could actually perform this task in general on a classical computer. And so this is one of the main motivations for why quantum computing is interesting. So the Hamiltonian simulation problem is concerned with simulating the time evolution operator here, given some description of h, a time of simulation, and some target error. We want to produce a quantum circuit that outputs a unitary that approximates this time evolution with very small error. So there have been many, so since it's a pretty important problem, this has been studied quite extensively by many people. Nathan is one of these people in the room. So though Feynman came out with the idea of simulating quantum physics on a quantum machine, Soufflé came up with the first explicit algorithm. In this case, we have an efficient specification of a Hamiltonian as a sum of small parts, where each part only acts on a constant number of qubits. This turns out to be universal in the sense that if you were to finding the ground state of such Hamiltonians is a QMA complete problem. And the cost of simulating the time evolution in this model is given by counting the number of exponentials you need. So you assume that each of these small components can be simulated efficiently. This was generalized to the d-sparse model because if you have a k-local Hamiltonian that acts on just a constant number of qubits, then this actually means that you have a Hamiltonian where you have d non-zero entries per row, where d is proportional to the number of terms here, but a constant in the number of qubits that each bit here acts on. However, this requires a slightly different input, whereas the k-local case assumes that each of these small exponentials can be simulated efficiently. Here we have an oracle which we can query to obtain the values and the positions of these non-zero entries, and the complexity is expressed in terms of number of queries to these oracles. So more recently, there was a new approach where instead of having the Hamiltonian specified as a sum of Hermitian operators, we can specify them as a linear combination of unitaries over here. And the complexity is then counted in terms of oracle queries to the coefficients here and an oracle that implements these unitaries. So even more recently, we had a new approach by Ceph again, where the target Hamiltonian is described as a density matrix. And instead of having an oracle that you would query coherently, this oracle just spits out a quantum state, which if you trace over like the ancillary register, spits out a density matrix. And so we count the number of samples of density matrices required to simulate the time evolution operator. So each of these simulation input models they can be applied to physics simulations, quantum algorithms, but so far in the literature, it seems like each model tends to be better for a certain application. Like the k-local case and the linear combination of unitaries case, it seems to be more tailored towards physical simulation of physical systems. And the d-sparse case is more tailored towards designing and analyzing quantum algorithms through quantum walks. And this case here, where H is a density matrix, seems to be tailored towards quantum machine learning algorithms. So all of these different input models naturally use different techniques for simulating the time evolution operator. So the case where we have a sum of Hermitian terms can be simulated using product formulas. The case where we have a linear combination of unitaries is simulated by truncating the Taylor series of the time evolution operator. The case of density matrices is implemented by performing a partial swap between the density matrix and the system on which you want to simulate the Hamiltonian. And the case where we have the d-sparse oracle is obtained by querying these oracles to obtain a quantum walk and then finding an appropriate linear combination of these quantum walks. So these different techniques, they all have different scalings because they address different problems. But the key factor to pick up from them is that the scaling with respect to the time of simulation here is, looks like this is dying, is almost linear. And it turns out that linear scaling in the simulation time is optimal. And additionally, the scaling in the error for some of these models is logarithmic here. So if you wanted to simulate your physical system with very small error, you can do it very efficiently. In this case, it turns out that these cases for the linear combination of unitaries and d-spars, they almost achieve this lower bound here, where you have, instead of it being multiplicative in the time and error, it is additive in the time and the error. And similarly, for the case of where the Hamiltonian is specified by a density matrix, you can also prove that this is optimal, although it is no longer linear in time. So in these algorithms, we can also look at the additional overhead required. So for these two algorithms where you almost achieve the lower bound, it turns out that you need a number of ancilla that scales with the problem size and the time of simulation. Now, all of these algorithms, they are simulated by different techniques. It would be pretty nice if there was a unified way to look at all of them, and also, more importantly, a way to achieve these lower bounds. So I will now talk about how we can actually do so by applying the ideas that we discussed earlier, where by choosing the right function on single qubit unitaries, we have a unified approach for some of these models. So in June, we came up with an optimal algorithm for the d-sparse model that achieves lower bounds. And the number of ancilla qubits, instead of scaling with the time and error of simulation, is just constant. And similarly, we can achieve the same for the case where our Hamiltonian is specified as a linear combination of unitaries. We achieve the lower bounds. And the number of ancilla qubits is now also just a constant. So these two, the improvement in the query complexity is not quite as exciting. It just goes from multiplicative to additive. But it's nice in that we can say that this is the best possible algorithm you can get for these models and these inputs. So, right.
What is the T?
So here in the complexity, we have the taus and the t's. For the d-sparse case, tau here is linear in the product of the time of simulation, the sparsity of your Hamiltonian, and the maximum value of any element in your Hamiltonian. The tau for the linear combination of unitaries is linear in the time of simulation and the product of this alpha here, which is the sum of coefficients in your linear combination.
In the mixed state model, it doesn't seem to make sense, right?
Yeah.
So, okay.
In the mixed state model, you just have a time t. All right, so a more exciting improvement is if we were to look at ways to improve the model where your Hamiltonian is specified by a density matrix. So the reason why this is exciting is because a lot of recent quantum machine learning algorithms, they use this input model where you have like classical data that is prepared into a form of a density matrix. So if you could improve on that model, then perhaps this could lead to generic improvements in all those other quantum machine learning algorithms. So the way we get an improvement is to use a different but still reasonable input model. In the case where rho is a mixed state and you get samples of rho, you still need to assume that rho is prepared by some quantum circuit. So while the density matrix, the mixed state, is obtained by throwing away the ancilla, it turns out that if we keep the ancilla instead, without actually doing any operations on it, or without knowing like its structure, just keeping it allows us to perform a simulation of its time evolution in a time that's linear in time of simulation and exponential in the desired error. So this is a quadratic improvement in time and an exponential improvement in error. And all of these input models actually turn out to be instances of a more general model, which we call the GUG input model. I'll talk more about this on the next slide, where the query complexity is linear in time and logarithmic in error, leading to all of these over here. So the general technique we do this comprises of two steps. Sorry?
Yeah, I have a question. So you say it's a quadratic improvement in T, and exponential, and epsilon, but it sounds like they're actually using two different query models.
Yes.
Is it clear that you what the complexity of simulating querying the purified Hamiltonian row oracle would be using the density operator?
That's a very good question. So in this case, this is motivated by how in recent machine learning algorithms, the density matrix is prepared by some data oracle. So this data oracle creates a superposition of the classical data states, but entangled with an ancillar register that indexes each of the data states. And you can get the mixed state by throwing away this ancillar. But creating this mixed state already requires that you have this oracle, so why not just directly use it without throwing away the ancillar? And so by doing that, you can get a different model where you can get some improvements. So in a different model, different problem, you might say that let's say we do not have the oracle that prepares the purified version of the density matrix. Then in that case, this will not be applicable. So it's a different set of assumptions, but it is still reasonable. And you can get back improvements by asking a different question. All right. So it turns out that the complexity of these algorithms, they exactly match a lower bound that you can obtain by solving parity. So in this case, you can find the parity of a bit string by mapping it to a Hamiltonian, which if you evolve for some time, gives you the answer with some probability. Like if you measure the output state, if it's 1, it says that your string has parity 1. If it's 0, it doesn't. And so in work by Barry, Childs, Cleve, Kothari, and Soma, they show that the lower bound is not exactly easy to interpret, but it is any number of queries q such that the target error is less than this value over here. And this n should be a q, that's a typo. The upper bound here is also exactly this, up to constant factors of e over 2. And if you were to expand this in the asymptotic regime for like large simulation times or small errors, we get the more recognizable and intuitive results here. So when the simulation time is bigger than the target error, it is additive in time and log of this. But if the simulation time is less than the target error, then you get something that's sublogarithmic. So this is just a more intuitive way to view this, but this is the true lower bound. And it matches this with just a constant factor of e over 2. So to show that this GUG input model is general, it contains the case of where you have the linear combination of unitaries, the d-sparse model, and the purified density matrices as a special case. To intuitively understand how this works, we have a unitary that in some basis has the target Hamiltonian here. So like you could imagine the unitary being comprised of two parts. You have an ancillar register and you have the system register. And now if you were to project the ancillar onto some basis state, you would get your target Hamiltonian here. And in terms of a quantum circuit, you would have the ancillar state prepared from some standard basis. You prepare this ancillar state that selects the right subspace of your unitary. You apply your unitary, and then you project back onto this ancillar. So if we have an input that is an eigenstate of this Hamiltonian here, we would get an overlap where this eigenstate here has now been modified by a coefficient that is exactly the eigenvalue because of this bit here. And then we have stuff that is everything else, orthogonal to this input state with some coefficients. So now if you want to think about applying the ideas of computing functions to this model, you could say that, well, maybe we could think of this coefficient here as a rotation angle. And if we could transform this coefficient into a phase, that is the time evolution operator, then basically we would have solved the simulation problem. But this input model is doesn't obviously have any structure that's isomorphic to single qubit rotations. And so we can overcome this by explicitly building this structure into our input model. So by lacking structure, what I mean is that you could specify your Hamiltonian in this way, but the oracle that contains it is a bit hard to analyze. You can't really say that the eigenvalues of this Hamiltonian are in any way related to this over here because you have all of these other terms here that are not really defined and are also hard to predict. And so if you were to apply multiple applications of this oracle, the desired components here, they would kind of leak into other states. So, there's a lack of structure here. It's hard to predict what happens. And we would like to impose structure here to make it so that multiple applications of our oracle can be easily predicted. And one ansatz is that suppose that we could create an oracle where instead of the target Hamiltonian being in just this top left block and the other bits being unspecified, if we could somehow create one where the target Hamiltonian was in these diagonal blocks, and then on the off-diagonal blocks we had some very predictable terms, it turns out that feeding in eigenstates of this Hamiltonian just reduces this to an SU2 rotation. Mm-hmm.
What exactly is the matrix on the off diagonals? Because it looks like it's a scalar.
Right. So this unitary has a component in this basis that is just H. And but this is just like one state amongst all of the possible input states of our unitary. So there would be many states here, like maybe all those perpendicular to G, but we do not specify them. When you implement a unitary that contains this element, these are non-zero, but we don't really worry too much about what they are. So this, if we could implement this has some very nice structure. Firstly, if we were to apply it to an input eigenstate, you would get the same eigenstate plus an orthogonal state. And then if you apply this unitary again, that orthogonal state would be mapped back onto our initial eigenstate. So because of this structure, it is easy to compute the eigenvalues of this unitary. And if you look here, you can see that it implements a phase that is nonlinear in the eigenvalues of our desired Hamiltonian. So in Hamiltonian simulation, we want to implement some desired time evolution where the phase is the eigenvalue times time. And this here now has an explicit dependence on the phase, the eigenvalues. This is not linear, but it's close. Perhaps if we could find a way to compute a function on this, a function that transforms this nonlinear phase in lambda to something that is linear, we would solve the Hamiltonian simulation problem.
I'm still also confused. What is the square root object here? How does it work?
Mm-hmm.
It's supposed to be an operator, isn't it?
You're referring to the W?
The square root expression.
The square root.
All
right. So in this case, we define it in terms of the eigenvalues. So if you feed in an eigen vector of H, then H on that eigenvector is lambda. So to interpret this, we imagine that this acts on an eigenvector, and so this becomes the eigenvalue squared. And then by superposition over the basis of H, we write W as a bunch of single qubit rotations, but the amount of rotation is controlled by the eigenvectors. All right, so if we could choose an appropriate transformation here, an appropriate function that computes this, we could solve the Hamiltonian simulation problem. And now that since this has a very nice single qubit structure, we can apply the ideas that we developed earlier of computing functions with single qubit rotations to implement this. So the way we do this is called quantum signal processing. So there are 3 steps. The first step is that we have our unitary W, which has very well-defined eigenvalues, and we make the controlled unitary. So we can think of this controlled unitary as feeding in an input that selects an eigenphase, and this eigenphase then determines what a single qubit rotation on the ancilla is. So we can map this onto the earlier problem of single qubit rotations by replacing each of these rotations where each rotates by an unknown angle theta with the controlled version over here. And so since the input state here selects the R rotation over here, we can think of it as computing a coefficient, computing a function on the ancilla, which if we were to project onto some ancillar basis, extracts some coefficients that are then applied to the input state over here. So this is like computing a function, modifying the coefficients on the input state, and by choosing these functions the right way, we could say convert the lambda we saw earlier for the eigenvalues and u to something that maybe is a phase. And if we could choose these functions that implement a time evolution operator, then it would basically be done. So we discussed earlier the query complexity of implementing some desired function using a sequence of single qubit rotations. Since we want to implement a phase transformation, if this phase here if this is a phase, so like its absolute value will be 1, and so this means that the success probability of post-selecting will also be close to 1. So this means that the issue of projecting onto an ancillar state to select the desired functions of our response function doesn't pose a problem. And we also had this theorem that talked about what are valid choices for A and C. So you want to choose A and C to be the time evolution operator. And though here we had A and C specified in terms of sine and cosines, this actually turns out to be just a Fourier series. A is a Fourier series in cosine, and C is a Fourier series in sine. And this constraint here just amounts to saying that we have a bounded Fourier series. So any choice of functions here that is bounded can be implemented. And if you want it to be a phase, well, that's bounded, so it satisfies this condition. And then the query complexity of implementing this phase would then be the best Fourier approximation to our function of this, will be the best Fourier approximation to this function as a function of the input phase. So in optimal Hamiltonian simulation, we just choose this function to be one that transforms this nonlinear phase in lambda to something that is linear in lambda. And the choice of functions that does this is choosing it to be t times sine of the phase. So if we were to look at the real and imaginary parts separately, then the real part here would be cosine in t times sine of theta, and the imaginary part is sine. So these are our target functions. And the best Fourier approximation to them turns out to just be the Jacobi angle expansion, which you can find on Wikipedia. And if you were to truncate these expansions to just a finite number of single qubit rotations, then the area of this truncation turns out to scale in this manner. But this exactly matches the lower bound that we saw earlier for the parity problem up to this constant factor of E. And so we can say that, well, by using this approach to compute a function that transforms eigenphasors, we can get an algorithm for Hamiltonian simulation that is optimal in all parameters. So this shows that by using the physics that we see in quantum control theory, there are ways that you can translate them to apply to quantum algorithms. So previously, quantum algorithms were mostly, they were mostly like very abstract. It was, aside from using physics to intuit some general guiding principles to their design, physics never really had a deciding role in creating like optimal algorithms with like best scalings in all parameters. But this shows that, with using some simple physics, we actually get the very best possible algorithms. And this suggests that maybe this is an overlooked aspect of algorithm design and how we can think of like novel ways to compile functions into fewer ancillar qubits. Like instead of transferring our intuition from classical computing, we could instead transfer our intuition from physics to such problems. So in related work, the time evolution operator is just one example of functions you could compute. Right now I'm working with Robin, Aram, and Ike to apply this technique to get quantum linear systems algorithm, which is inverting a matrix. And it turns out that we can get one that is optimal in all parameters as well, with matching lower bounds. So this is pretty general. You can choose any function, and we hope that this applies to more problems like Gibbs sampling and so on. So on the more applied side, we have this methodology to compute single qubit functions that can solve interesting physical problems. And so we are working on realizing these in Lincoln Labs. So all of this work kind of provides a new way to think about how we can design some algorithms. And in terms of the results itself, they lead to better ways to simulate problems like in quantum chemistry and also in machine learning. So those are two things which I'm very interested in and looking at right now. All right. Thank you very much.
Okay, we're running out. We have about 2 minutes, so I'll take one or two questions.
Because I haven't asked any questions so far. I'm curious, from quantum simulation, one of the problems I ran into when I was looking at trying to apply more recent techniques to this is that there's a lot of difficulty in applying the quantum oracle that ends up outputting the coefficients. I was wondering if this method runs into those same sorts of problems that most of the linear combination methods do.
So to answer the linear combination of methods problem, so I guess it is similar to the case where you specify Hamiltonian as a linear combination of Hermitian matrices. It is input model dependence. So like it depends on the problem. Like let's say in one of your recent papers, you were looking at the complexity of quantum simulations in real space. And the difficulty you encountered was that you had the potential operator, and then you had the kinetic energy operator, and it's kind of hard to translate this into like what the unitary is. So that is one approach to the simulation of physical systems. In another approach, we instead use some efficient classical computation to map like a quantum chemistry problem onto a well-defined set of bases with a list of coefficients. So that those coefficients could then be, since it's a classical list of numbers, you could then implement it using a unitary that you could compile from this list of numbers. So like it depends on the input model. In some input models, it's hard to find the direct analog of these unitaries. In other input models, it is easy. So here we have a new input model, which is quite general as a GUG input model, where our Hamiltonian is just the projection of the unitary, and maybe this could lead to different ways to specify your Hamiltonian. Maybe it could lead to a more intuitive way to reconcile the problem of finding these real continuous variable operators to their like discrete unitary counterparts.
Any other questions? Otherwise, we're at time, so let's
All right.
thank you again.
Thank you very much.